We now move into the next part of this chapter, which is general states, continuous spectra, and bound and unbound states. Up to this point, we have mainly discussed eigenstates of Hermitian operators, their real eigenvalues, orthogonality, and completeness. That framework is extremely important, but so far it may still give the impression that the most interesting states in quantum mechanics are always eigenstates. In practice, however, a quantum system is often not in an eigenstate of the observable we choose to measure. So the first question we address here is this: how do we describe a general state that is not an eigenstate of a given operator? The answer will be to expand that state in terms of the complete set of eigenfunctions of the operator. Once we do that, the expansion coefficients acquire a direct probabilistic meaning. Then we move on to a second important issue. So far, most of our discussion has been framed as if the spectrum of an operator were discrete, like the energy levels of a bound particle in a box. But not all observables have discrete spectra. Some observables, such as the momentum of a free particle, have a continuous spectrum. In that case, the mathematical structure changes in an important way. Sums become integrals, Kronecker deltas become Dirac deltas, and the eigenfunctions are no longer square normalizable in the ordinary Hilbert space sense. Finally, we will distinguish between bound states and unbound states. That distinction is physically important. Bound states are localized and typically associated with discrete spectra, whereas unbound states are extended or scattering-like and typically associated with continuous spectra. So this part of the chapter is important because it broadens the picture. Quantum mechanics is not only about determinant eigenstates, it is also about arbitrary superpositions, statistical outcomes of measurement, and the different mathematical treatments required for discrete and continuous spectra. Let's now consider a state that is not an eigenstate of the operator A hat. In other words, the state doesn't satisfy an eigenvalue equation of the form. So what do we do in such cases? Consider a general state psi that doesn't satisfy the eigenvalue equation for the operator A hat. Assume this operator has a complete orthonormal set of eigenstates, as shown here, with each one of them satisfies the corresponding eigenvalue equation. And of course, these eigenstates or eigenfunctions must satisfy the orthonormality condition as shown. Now suppose a general state psi is expanded as shown here, which is a linear combination of all the eigenstates. Its bra is obtained by taking the adjoint as shown here, where we apply complex conjugation to the scalar and change the ket vector to its corresponding bra vector. So the key idea is that although psi itself is not a determinant state of the operator A hat, it can still be decomposed into determinant states of the operator. Now let's calculate the expectation value of the observable A in this general state. By definition, it is given by this formula. Substituting kit psi and bra psi into the formula given here, we get a double sum over basis functions or eigenfunctions as shown. Then, because each phi sub I is an eigenfunction of the operator A hat, we replace the operator A hat acting on the ket vector phi sub I by lambda I times the ket vector phi sub I. After that, orthonormality simplifies the expression and all cross terms vanish. So what remains is the expression shown here, or the equation shown here, to be more precise. This result is extremely important. It tells us that the expectation value of the observable is a weighted average of the eigenvalues with weights the absolute square of the coefficient C sub I, where C sub I is the inner product of the eigenfunction with the general state psi. So even when the state is not an eigenstate, the eigenvalues still play the role of the possible definite measurement outcomes, and the coefficients determine how those outcomes contribute statistically. This is the first form of what is often called the generalized statistical interpretation. A general state is a superposition of eigenstates, and the expectation value is the weighted average of the corresponding eigenvalues. Now we ask a crucial question. What is the physical meaning of the expansion coefficients C sub I? The previous slide already suggests the answer, because the expectation value came out as shown in this equation, which already looks like a statistical average, as we have already mentioned on the previous page. Here we just need to justify it more rigorously. So first, we assume that the wave function psi is normalized. Then the inner product of psi with itself must be equal to 1. Using the expansions of bra and ket vectors psi, we obtain this expression. Since the eigenfunctions form an orthonormal basis, they must satisfy the orthonormality condition. We know that the inner product of phi sub j with phi sub I must be equal to delta sub ji, and since j runs over all indices, whenever j equals I, delta sub ji is non-zero. So this expression is reduced to the expression shown here. So we remove the summation over j by applying the orthonormality condition. As a result, the absolute square of the expansion coefficients are non-negative and sum to 1, as shown in this equation. Mathematically, they have exactly the structure of probabilities. Now comes the physical interpretation. When we measure the observable associated with the operator A hat, the initial general state does not itself give a definite value. The act of measurement else one of the eigenvalues lambda sub I, and the state is then found in the corresponding eigenstate phi sub I. Therefore, the absolute square of the expansion coefficient C sub I represents the probability of finding the state psi in any one of the eigenstate phi sub I after the measurement has been made on psi. In other words, we interpret the absolute square of the expansion coefficient C sub I as the probability that the measurement outcome is lambda sub I, and the state psi is in the eigenstate phi sub I. The coefficient C sub I are called probability amplitudes, and their absolute squares are the actual probabilities of the various measurement outcomes. In fact, this is a very important extension of the Born interpretation. Earlier, we interpreted the absolute square of psi of R and T as a probability density in position space. Here we are saying something more general. If a state is expanded in the eigenbasis of an operator corresponding to an observable, then the squared magnitudes of the expansion coefficients give the probabilities of obtaining the corresponding eigenvalues upon measurement.